Today we start thermochemical changes in Chemistry 30, Unit 2. Our job is to track how energy moves during reactions between a system and its surroundings and connect it to real processes like photosynthesis, cellular respiration, and combustion. Thermochemistry focuses on energy absorbed or released during chemical reactions. Even calm-looking reactions involve energy. The difference is how that energy is transferred. As we go, keep asking one question. Where is the energy going?
Chemical bonds store potential energy. Breaking a bond requires energy input. Forming a bond releases energy. The overall energy change depends on the balance between energy required to break bonds and energy released when new bonds form.
In reactions, energy is not created or destroyed, it is transferred between the system and the surroundings. Because energy changes are measurable, we can quantify and predict them and later connect them to enthalpy and Hess law calculations. Reactions are classified by the direction of energy transfer between the system and its surroundings. The key is not whether energy is involved, but where the energy goes. Exothermic reactions release energy to the surroundings, usually as heat so the surroundings warm up. Combustion is the classic example. Fuel burns and stored chemical potential energy is converted into thermal energy that warms the environment. Endothermic reactions absorb energy from the surroundings. Energy must be supplied for the reaction to proceed, so the surroundings often cool down. Cold packs pull thermal energy away from skin. Photosynthesis is another key endothermic process.
If the reaction mixture feels cooler than the surroundings, heat is flowing into the system, so it is endothermic. If it feels hotter, heat is flowing out of the system, so it is exothermic. Through it all, energy is conserved. Total energy before and after is the same overall.
Energy diagrams give us a visual model that links collisions, bond energy changes, and temperature effects. They help explain not just what happens, but why reactions can occur at different rates.
On an energy diagram, the vertical axis represents potential energy. The horizontal axis shows reaction progress, not time. The peak is the activation energy barrier. Compare the final energy level of products to reactants. If products are lower, energy was released overall. If products are higher, energy was absorbed overall.
In an exothermic profile, products end lower than reactants, so the overall energy change is less than zero. In an endothermic profile, products end higher than reactants, so the overall energy change is greater than zero. A reaction does not create or destroy energy. It transfers energy between the reacting system and the surroundings. Whether it feels hot or cold depends on the direction of that transfer.
Define your system as the reacting chemicals. Everything else is the surroundings, including container, air, and measuring devices. In an exothermic system, energy leaves the system and enters the surroundings, so temperature around it increases. In an endothermic system, energy is absorbed from the surroundings, so the surroundings cool. Temperature tracks average kinetic energy, while enthalpy change describes the total energy change of a system.
Step 1. Observe the temperature change. Did the surroundings gain energy or lose energy? Step 2. Classify the system. If surroundings warm up, the reaction is exothermic and the enthalpy change is less than zero. If surroundings cool down, the reaction is endothermic and the enthalpy change is greater than zero. A simple diagram is a single-step reaction with reactants, a transition state, and products. A complex diagram is multi-step, showing intermediates and multiple energy barriers. Look for the highest barrier. That is often the rate-limiting transition state because it is the hardest step to get over.
Create dynamic, powerful, and informative videos with an avatar as your host. Instantly translate your video into over 80 languages. Use engaging media to grab your audience's attention, or even simulate conversations between multiple avatars. All with an intuitive interface that anyone can use.
A catalyst increases the rate of a chemical reaction without being consumed. It works by providing an alternative pathway with a lower activation energy. Think of it as a shortcut that still ends at the same destination. First, catalysts lower activation energy, so more collisions have enough energy to react. Second, catalysts do not change the enthalpy change. They change how fast the reaction occurs, not how much energy is produced or absorbed. Third, catalysts are regenerated, so they are not used up overall. In industry, Catalytic converters use platinum group metals to convert toxic exhaust gases into less harmful substances. The Haber process uses catalysts to make ammonia at large scale. In biology, enzymes are highly specific catalysts that let life reactions happen quickly at body temperature. Without them, reactions would be far too slow to sustain life. Thermochemistry matters because energy changes affect technology, the environment, and society. Energy efficiency is about converting energy input into useful output. Catalysts improve efficiency by allowing milder conditions and reducing the energy needed to initiate the process without changing the enthalpy change. Moving forward, these ideas set us up for quantitative energy calculations, Hess law, and real-world energy analysis.